So my talk today is probably quite different from the other ones because I will not be speaking about an existing facility or even a scheduled one, but rather it belongs to the blue sky thinking process because the community is currently, the astronomical community is currently very busy building big stuff. And I think we are several to think that it is a good time to invest in research and development in instrumentation. So this presentation, I prepared this presentation with Guillaume Bourdarot, who is a PhD student finishing here in Grenoble. So the idea of using mid-infrared interferometry is not new. It has been demonstrated by the Charles Towns and Bill Danchi group at ISI in Berkeley, and later resurfaced with Andreas Eckert and the University of Cologne expertise and Ernest Michael in Chile. And what I would like to talk to you today is, first of all, what is the inspiration and what would be basically the next interferometry facility that would allow to bring an order of magnitude improvement in our understanding of planet formation studies, and also provide a sense of optimism and by showing that technology today has advanced to a level where we can actually believe that mid-infrared heterodyne technology might be the way to go, at least for many telescope interferometry. So the inspiration of this work started in 2013 at the OHP and was basically inspired by, and it's still inspired by the amazing results obtained with facilities such as ALMA, Plateau de Bure, and extreme adaptive optics that have revealed the complexity, the large-scale complexity of protoplanetary disks, but also at the same time show their limitation, but not allowing to actually observe directly the inner astronomical units where most of the planet formation processes occur. And we know that indeed many of the systems that are observed today, the evolved systems, have initially come out processes occurring in the inner 10 astronomical units that involve, of course, planet accretion, planet formation, but also giant planet migration and dynamical instabilities. And all these processes are known to occur very rapidly, and therefore you need to capture these processes, the regions where they occur, which is basically up to 100 parsecs. So if you want to observe planet formation processes at a few hundred parsecs, you need a specifically new facility. And that's where the motivation to explore a mid-infrared facility comes from. So just to remind you that imaging and mapping young stellar objects has already been done, and thanks to ESO facility, and you've seen the potential of Matisse this morning, and you've seen already a very nice images. The VLTI has already been used through a large program to observe the inner dust sublimation of protoplanetary disks. And you have here a mosaic of images from a paper by Kluska that shows that you can really clearly see and map the dust sublimation frontier, but that shows at the same time the limitation of imaging with 4 telescopes, which restricts the complexity of the image you can reconstruct, but also, as you can see on the right, where we try to explore what was the dynamical range in search for features such as dynamical deformation, ice lines. And you can see that the current performances of instruments does not allow to go much further than a few percent, which is not compatible with deep planet formation studies. So you need really to go beyond that. And that was the motivation for the planet formation project, planet formation imager, which was led by John Monnier, Stefan Kraus, and Mike Ireland, and several working groups. And that asked the question, what would be the facility that would be able to image the key stages of planet formation? And this work has been carried by quite an extensive science working group, and in particular has based its conclusions on the analysis of simulation, hydrodynamical simulation and radioactive transfer that have essentially captured the planet formation processes. And the ambition of such an interferometer, in order to go well beyond what ALMA or SPHERE, for example, produce, would be to be capable of actually resolving planets in the disk, resolving the dynamical structures around planet, resolving the ionosphere and the kinematics of circumplanetary disks. And as you can see on the right on this simulation of the same disk at different wavelengths, depending on the wavelengths you observe, you will be sensing different parts of the disk and also different types of dust. And for what we're interested in, basically the 3, 5 to 24 micron of the Q-band is the way to go. So basically the most basic top-level science requirements for such an interferometer would be to be able to characterize young exoplanet up to Taurus, to resolve circumplanetary disks, which means a few milli-arcseconds in the mid-infrared, spatially and kinematically, which is important, and also mapping dust distribution, which points at several telescopes. So the team led by John, Stefan, and Mike have done an extensive work, and there are several papers that you can consult if you're interested, to basically provide a baseline specification for such an interferometer. And if I could summarize the study, you've basically, you're thinking of two types of performances. First, you need imaging capability, real imaging capability in the mid-infrared, mostly between 13 to even 20 microns in order to spatially resolve the ionosphere around protoplanets. But if you're interested in actually detecting young planets, the way to go is probably to go to the 3 to 5 micron bands, and you've heard about Denis de Frère and its precursor sci-fi instrument. And when you turn that, and in particular the surface brightness into specification, you come up with a requirement that involves many telescopes, at least 12, at least 3-meter diameter, even if that number is probably underestimated, kilometric baselines, and the need for also to co-phase that. And that's the result of the PFI analysis. So you can really see what they came up with. It's interesting to see that we're not far from having the technology to do that. So what I would like to now talk is really about the technological advances. I'm not going to talk about direct interferometry. You've heard of that. You see that it works. You've seen Matisse. Really nice results. So direct interferometry is just about interfering two beams coming from two telescopes and physically matching them onto a detector. That sounds simple, but it's not simple in reality. Heterodyne interferometry has a different philosophy. The idea here is to completely relax the infrastructure requirements and rather distribute a local oscillator. I don't know if do I have my, I don't know if you see my pointer, probably not.
We can see the pointer.
Okay, and the idea is really at each telescope level to interfere the incoming beam with what is called a local oscillator, and something that is something that is done since decades in the radio domain, and use the beating signal, what is called the intermediate signal, to encode the incoming electromagnetic field amplitude. And once you have this intermediate signal, you propagate that into up to a correlator that will take care of extracting the meaningful information. So what you see here on the right is really basically the scheme. It's a basic interference between the local oscillator and the incoming beam. And what you get out of that is basically you down convert the frequency, the high frequency, mid-infrared frequency at the level of several tens of terahertz to intermediate bands. So one of the difficulties that has been well identified since a long time is that if you want to do heterodyne interferometry in the mid-infrared, you're facing an increasing difficulty with quantum noise. And this has a dramatic effect. It's related to the fact that you have much less photons per mode when you're going to shorter wavelengths. And this is something that Charles Towns really understood. You have here his handwriting showing that basically if you really want to compare direct to heterodyne, you really need to start at basically at 10 microns to have heterodyne competitive. This number is of course sensitive to hypotheses, in particular the global throughput, and depending on the direct interferometry throughput efficiency, you could have basically even heterodyne outcome at these wavelengths direct interferometry performance. So mid-infrared is really the regime where these both compare. So if I summarize the advantages of the two at the moment, and as it is analyzed in the PFI reports, with direct interferometry, you have on paper performances that is intrinsically more sensitive, probably simpler instrumentation, broadband operation, but quite complex and expensive infrastructure, and of course a loss of sensitivity with a number of telescopes, which is something you don't have. Heterodyne is intrinsically probably less sensitive because of quantum noise. It's narrowband. It requires probably a more complex instrumentation, but the infrastructure is completely relaxed and better adapted to a high number of telescopes. So just to keep the motivation, just to remind you that ISI, the infrared space interferometer, worked. You have here a visibility curve obtained on a very high source, but the visibilities were extremely precise, comparable to what has been done in direct interferometry in terms of accuracy. And the question now is, how can we go beyond? Can we extrapolate this to a higher number of telescope facility? And basically, there is a consensus among people that are thinking about how to expand heterodyne interferometry is that, first of all, you need to increase sensitivity. And for that, and if you compare to the 3 gigahertz bandwidth of ISI, you need first to increase the bandwidth, and you can do that through innovative new detectors. And you need also to increase the bandpass by using laser frequency comb that allow you to have several combs of coherent light phased between them that allow to sample a much broader bandpass. So the vision that we can see for an infrared heterodyne interferometer for many, many telescopes is, and kilometric baseline is something that would look like that. You have several telescopes. Each telescope is equipped with a system that allows to interfere the incoming signal with a local oscillator. The local oscillator is laser frequency comb, and you have to bring back the signal to a correlator. So this is not new. This is comparable to radio, but the technology is completely different. And the vision we have, and I'd like to convey, is that today the technology has progressed in such a way that we would probably consider that all the links between the telescopes could be completely integrated into a fiber link. No local oscillator, mid-infrared local oscillator propagations, such as in ISI, just purely fiber links. So what are the challenges to develop that vision? First of all, like any N telescope interferometer will need low cost telescope in order to bring down the cost. You need sensitive high bandwidth detectors. You need mid-infrared frequency comms, efficient, cheap, high resolution spectrometers. And also you need to phase lock these local oscillator over kilometric baselines. And you need correlators capable of handling many telescopes and 40 gigahertz signals, which is currently would require, if you extrapolate, for example, from the ALMA technology, would require very expensive computing power. So there are several ongoing technological efforts. You will hear Amelia talking about interesting development in the field of carbon fiber mirrors. There are work at JPL on mid-infrared frequency comms, and Ernest Michael's group in Chile is actually really advanced in developing a near-infrared prototype, and also is collaborating with the University of Köln, has very long experience in heterodyne. So what I would like to focus now is what we are doing mostly on our side in Grenoble with our collaborators, and also to convey, like I said, really optimism about how the technology is going. So I will not go in the laser frequency comm domain. There's a huge amount of body of literature. Just to remind you that we have specific constraints. So not all the not all the frequency comms work. We need very specific comms with wide separation, 10 gigahertz comms. but you have to know that this is currently not a showstopper, and there are solutions that could be investigated. In the field of detectors, the last decade has seen an explosion of new developments, mostly driven by the need for spectroscopy and even quantum information propagation. I've extracted a few of the recent headlines showing that in laboratory detectors with several tens of gigahertz bandwidth and not so bad quantum efficiency, even if that can be increased a few 10%, have been developed. So that's what we. I mean, that's a very important news in this field, because these are one of the key points of the whole instrumental chain. And just to show you advances from our collaborators at Laboratoire de Physique de l'École Normale de Paris, you have here the demonstration of a heterodyne detection scheme using a very fast, high bandwidth detector, quantum well infrared photodetector, and QCL that allow to basically demonstrate stabilization of the of what we would call the local oscillator to bandwidths of a few hertz, which shows that we can actually deliver both at the detection scheme and use this detection scheme to stabilize a local oscillator very nicely. The second very impressive development that we're starting to explore with our collaborator at CIRT in Paris has been the demonstration that a laser, a mid-infrared laser that you can see down on this figure, could be synchronized with atomic clock at 43 kilometers. And I will not go into the detail of this scheme, but you have basically an atomic clock at CIRT. And this atomic clock is used to lock ultra-stable laser in frequency. This ultra-stable laser is stabilized, propagated over 43 kilometers, and then is used to basically lock locally mid-infrared laser, and therefore provide a synchronization, a phase synchronization, phase stabilization, which is incredibly higher than what is needed for heterodyne VLTI. And it's actually working. So this is a very nice work by the equipe of Chanteau and Argens at CIRT, and that provides the demonstration that you could even already consider having these links at kilometric distances. So here in Grenoble with our collaborator Hugues Chateluz, we've been exploring one of the other challenges I mentioned before, which is the challenge of correlation. I said that we need a very high bandwidth detector in order to increase the sensitivity. And what we have here is basically what we have been demonstrating, that was a work of Guillaume, is that you can actually not use the standard radio frequency correlation technique, but rather encode the signal a laser carrier. And I will not go into the detail of this combination, but just the important thing to notice here is that we convert the down-converted intermediate frequency signal into a laser signal that can be combined using classical photonic technology. And the interesting aspect here is that you have a monochromatic signal that you can amplify, so you can divide it depending on the number of telescopes, and still interfere it in a classical way. And Guillaume demonstrated nicely that you can recover you can actually measure the coherence of the light, you can explore the coherence of the source. So it's actually an operational system. It's not new, it has been used in different contexts in the military, but never in this context of correlating astronomical signal. So this schematic, this idea of not using an actual computer to do the correlation, but rather an analogical correlation is certainly something to be taken very seriously, as it would relax considerably the cost of the infrastructure, and provide also a way to transport the signals from the telescope in a fiber link. So what we have in mind now, and what we are building, is a prototype instrument that would combine two telescopes And you have here basically a schematic. The light from two telescopes would come, and it interferes with the laser oscillator, laser locked oscillator that I described before, and provide two intermediate frequency signal that we would correlate. And the reason why we want, yes, thank you. The reason why we want to do that is we would like to use that prototype to the demonstrator and bringing on the sky to demonstrate the full performance and actually confirm the signal to noise estimation that we are doing in the paper, and that show that with this kind of system, with this kind of performances, we could probably improve over the ISI and therefore demonstrate that the technology is worth exploring for more telescopes. And what we have in mind, of course, and at the moment it's completely a pure speculation, is to provide VLTI with an instrument that would be capable of combining the 8 telescopes. As you may know, it's impossible at the moment because you have only 6 delay lines. But with heterodyne interferometry, the optical path control is integrated into the correlator. And as we've been using Antoine Méran's very nice publicly available code to simulate the sky coverage that you would get with 4 telescopes. And it's actually very nice. Of course, an instrument based on heterodyne interferometry without phase tracking would be not super sensitive, but would allow to many bright targets and in particular do imaging, snapshot imaging of many bright targets, because you would have 8 telescopes, so much more baselines, and you have a simulation by Guillaume showing that the signal to noise is in a coherence time in integration of 4 times 5 minutes is absolutely decent and would allow to provide narrowband imaging of bright stellar surfaces. So I will finish by wrapping up and just to remind that since the astronomical community is busy building big telescopes, big infrastructure, now is really a good time to invest in interferometric research and development, whether heterodyne or direct interferometry. We are now convinced, I didn't have time to show you the signal to noise computation, but that mid-infrared heterodyne interferometry is very likely competitive, in particular when you have more than N telescopes, and in particular in the N and Q bands. Both direct and heterodyne need cophasing. I didn't mention that, but it's still an open problem, not a showstopper, but still an open problem. The positive thing is that the global physics and industry research and development is pushing in the right direction: detection, laser comms, phase locking, computing power. And our proposal, which is very preliminary, would be to use heterodyne interferometry to combine simultaneously the 8 VLTI telescopes. That would be a pathfinder for future instrumentation, and at the same time provide great imaging capability for bright objects. And I'd like to finish advertising a workshop that never happened. It was a workshop that we organized last March, and we had to cancel for reasons you well know. And we will probably, we will most certainly reopen it. So stay tuned for the announcement. And this is a workshop dedicated to putting together different technology specialists and having them brainstorm around the development of this very nice technology. Thank you.
Thank you, Jean-Philippe, for this very inspiring talk. There are some questions. One from Olivier Absil, which is, what are your plans on sky demonstration? You said VLTI, but timeline?
Okay, so at the moment, the only thing we believe the master is the 2 telescope combiner, because we have almost everything to put it together. So one thing we would like to do is to bring that on sky and convince ourselves that we master all the noise figures down to the level where a more ambitious project interesting. So at the moment we are building that thing, and that will be the rule, and that would set the rule if we go or not. that will be the milestone.
But do you have an estimate for the dates of this two telescope prototype?
2 to 3 years, because we need the development of the high bandwidth detector at Paris.
There is another question, which is, if you cannot go to the VLTI, do you have another site in mind?
Well, one of the first things we could think of is using a single telescope, and then our options expand. We've been exploring also lately the use of the C2PU telescope at Observatoire de Calerne. So we've been there. It's a very nice infrastructure with 2 telescopes closely spaced. It's the Heterodyne experiment by Jean-Guy. At the moment, we have doubts that transmission at 10 microns would be effective. So we have a sample of the mirror, and we have to test it in order to know whether we can test that instrument there.
Apparently, there is no new question. I have one question. I tried a little bit to go through the SNR calculation of Ernest Michael, and it seems that the conclusion was that it needs to reach 100 gigahertz to be competitive. You mentioned at 40. Does this come out of your computation? I mean, what do you think about this discussion?
Yeah, okay, so this could be a very long discussion, because Ernest is also advocating at the same time that you can beat quantum noise by a correlation. So I'm not sure I see the number you refer to, because I was under the impression that he stated that we could do that with lower bandwidth. I could show you, so I don't have time, but this is a computation by a plot that is not immediately accessible, but just to show you that Guillaume did a computation showing that you have basically the ISI performances, you have the Matisse limitation at 3 sigma, and showing that on paper, with these numbers are the instrument we're talking about here. On paper, we have a sufficient sensitivity with 20 gigahertz to carry on meaningful science information. But so I don't think the 100 gigahertz baseline, as we know, ISI work with 3 gigahertz. So it really depends on the objects you want to observe. But even with 10 gigahertz, 20 gigahertz, you could already do something.
A question from Hendrik Lins. Is heterodyne interferometry currently the main path for thinking for the planet formation imager that drives the project, or is it a more potential far future option for PFI?
Yeah, it is not at the moment. At the moment, the main direction is direct interferometry. And like I said, I mean, at the moment, Heterodyne has to prove it has the sensitivity, and that's why we need to tackle all the technological challenges that I mentioned. But the motivation to do that is that when you extrapolate from what is existing, we believe we are competitive. But Heterodyne has to prove it.